So what we are doing today is, like I said, it's an extension of what we've been doing. But ultimately we're just using fundamental trig identities. And most of the ones we're using, you guys have already seen. Like, you've seen the reciprocal identities. Reciprocal. Which are like sine of theta equals 1 over cosecant of theta. Cosine of theta equals 1 over secant of theta. Tangent theta equals 1 over cotangent of theta. And then you've got their opposites, right? Where you've got cosecant of theta equals 1 over sine theta. Secant theta equals 1 over cosine theta. I'm writing them all out because you're going to need them here in a minute. Cotangent of theta equals 1 over tangent of theta, right? And you've seen those. You also had the quotient identities. There were only 2 quotient identities. One is that tangent of theta equals sine of theta over cosine of theta. And then its inverse, which is cotangent of theta equals cosine of theta over sine of theta. I think the book is using u in this section instead of theta, but it doesn't matter. It's still just a variable for a measure of an angle. So if you see tangent u or something like that, just remember it's the same as theta. It's just a variable. We're just using a different one. And then you had your Pythagoreans, Pythagorean, right? And you have your standard, which is sine squared of theta plus cosine squared of theta equals 1. That's the one you're going to see the most of always. You have 1 plus tangent squared theta equals secant squared theta. And you might see these in a different order, right? If I have, say, -1 on the side of that other side with that secant squared, it's still going to equal tangent squared of theta. It's still that Pythagorean identity. And then we have 1 plus cotangent squared theta equals cosecant squared theta. And those are the ones you've seen. We're going to add a couple more that you haven't seen now. So the ones that you haven't seen are the cofunctions, which you've seen a variant of them because you saw it with degrees, but now we're going to be doing it in terms of radians. So if we have sine of pi over 2 minus theta, or in your book it might say minus u, it would equal cosine of theta. If I have cosine of pi over 2 minus theta, it is going to equal the opposite, right? It's going to be sine of theta. Now, memorizing these things is great, but ultimately, you're going to have a list in front of you when you're using them. And I always recommend having all of your identities in front of you when you're doing identity type problems. Then we've got tangent of pi over 2 minus theta equals cotangent of theta. We've got cotangent of pi over 2 minus theta equals tangent of theta. And then we've got our last two. We have secant of pi over 2 minus theta, you might guess, equals cosecant of theta. And then you have cosecant equals secant, right? I was looking at my paper and I saw the ones below it. And I'm like, that doesn't look right. It's because I was mixing up the two sections. And so you can see that they're kind of inverses of each other. And we worked a little bit with that. We had the 90 degrees minus theta, and they worked out the exact same way. And last but not least, we have the even odd functions. And these really help us with signs when we're dealing with signs of stuff, when we're factoring these things out and trying to solve them. So if I have sine of negative theta, I could write that as negative sine of theta. If I have cosine of negative theta, I write that as positive cosine of theta. With cosine, the negative doesn't transfer. So if I have cosecant of theta, which is the inverse of sine, we're still going to get the negative. But if I have secant of negative theta, we're just going to have positive secant of theta. In all honesty, all you need to remember is that cosine and secant, if you have a negative theta, translates to a positive. The rest of them will all be negative. If I have tangent of negative theta, I get negative tangent of theta. If I have cotangent of negative theta, I get negative cotangent of theta. So all you really have to remember when you're looking at these is that if I have a negative on my theta, and it doesn't matter what that theta is, it could be negative pi over 2, right? This would wind up being negative sine of pi over 2. If I had 3 pi over 4, negative 3 pi over 4 tangent of, it would be negative tangent of 3 pi over 4. Where if I had negative 3 pi over 4 here, it would just be cosine of 3 pi over 4. That's all that's going to look like. And the only time it comes back positive is when you're dealing with cosine or secant. So we're going to look at some examples of how these play out, because what we're going to be doing is using these identities to evaluate our functions, right? Using identities to evaluate functions. When you do these, as always, you must show work. If you just give me an answer, I'm kicking it back to you, right? The reason I'm having you do this on paper is to see the process, and I'm grading that more than the answer. I would rather you show me that process that you used and get the wrong answer than just give me an answer. So our first example is we're going to be given that secant u, right? U is just our variable, equals negative 3/2. And it's also telling us that tangent u is greater than 0. So we need to look at where is tangent going to be greater than 0? Where is tangent positive? And there are only 2 areas where tangent is positive. When they're both positive, when x and y are both positive, or when x and y are both negative. So here, tangent would be positive, and here tangent would be positive. And since we know that the secant has a negative, we know that we're dealing with quadrant 3, right? Because here there are no negatives. And for us to have a negative secant, we'd either have to have a negative x or a negative y. Technically, we would have to have a negative x, right? Because secant is like cosine. It plays off the x. It's like 1 over the x value. So we know that this is going to be in tangent 3. And the reason we need to know that is we need to know how to apply our signs to our trig functions. Because what we're going to do is we are going to find the other 5 trig functions, right? Based on this piece of information. And we've done this before. We were doing this kind of stuff before. So we're going to go through them one by one. Let's write them out here. We know the first one is going to be secant equals negative 3/2 because it was given to us. We need to find out cosine, sine, cosecant, tangent, and cotangent, right? And we're going to start with cosine. And the reason we're going to start with cosine is that I know that secant of u equals 1 over cosine of u, using my trig identities, right? It's one of our reciprocal identities. I'm going to rewrite that, though. I'm going to rewrite that as cosine of u, because that's what I'm trying to find, equals 1 over secant of u. Same thing, right? It's just the opposite identity. And I know that secant of u equals negative 3/2. So I'm going to write that as 1 over negative 3/2, which is the same as saying negative 2/3, right? Because if I multiply 1 over 1 times the reciprocal, which is negative 2/3, I get negative 2/3. Now, I don't even really have to think in terms of positives and negatives right now, because we're going to have to go through and attribute that at the end based on where we're lying in the quadrant, right? Is it an x or is it a y? So what we know now is we know our cosine and we know our secant. We can find our sine using the Pythagorean identity, right? We have the one identity that says sine squared of theta plus cosine squared of theta equals 1, right? And in this case, our u is our theta. So I could go, okay, well, I know that cosine of theta is 2/3, right? So I could go, well, sine squared of theta plus 2/3 squared equals 1. And then we can just go ahead and solve for sine, right? We get sine squared theta plus 4/9 equals 1. And we can subtract that. Whoops. Looks like I wrote 9/9, but it does say 4/9. It's just a fat pin. So we can subtract that 4/9 from both sides. And I would get sine squared of theta equals 1 is 9/9 minus 4/9, which gives me 5/9. Now notice that's giving me sine squared of theta, and I want to know what sine of theta is. So I'm just going to take the square root of both of those, and I'll have that sine of theta equals the square root of 5 over 3. And I can just write that over here for now. Now, looking at this, the others are a little bit easier to find, right? I've found, once I find that sine and cosine, I can pretty much find anything else just based off of those. I know that cosecant of theta equals 1 over sine of theta, right? And I know that sine of theta is just radical 5 over 3. So I could write this as the reciprocal, right? Because that 1 over 3/5 is just going to flip this around. So I would have 3 over radical 5, but I can't leave it like that, right? I have to rationalize that denominator, and I would get 3 rad 5 over 5. Now, tangent, we know, is a quotient identity, right? Tangent is sine over cosine. So that would give us radical 5 over 3 over negative 2/3. And like I said, we don't need to play with the negatives so much right now, because we'll know what sign to attribute to it based on the fact that it is right here. And they will wind up being positive because our x and y are both negative right here. So tangent and cotangent are going to be positive in this quadrant. And so we're just going to go, okay, well, we've got our tangent. So we've got radical 5 over 3 times the reciprocal, which is 3 halves. And I could cancel these, and I would get radical 5 over 2. And we know that cotangent is a reciprocal of tangent. So cotangent equals 1 over tangent, which is rad 5 over 2. And so that would just be its reciprocal, right? We would have radical 5, we would have 2 over radical 5, and we would have to rationalize that denominator, and we get 2 rad 5 over 5. So you guys have done this stuff before. I did one more example of this type, but I'm going to go ahead and move on to the next section to keep the video kind of short. But if you guys want to see the other example that I did, I can do it afterwards. But it follows the same kind of pattern where we're looking for all 6 trig functions using the identities. Let's see. Our next bit is we're just simplifying, right? So in the last one, we were finding all the trig identities, all the trig functions using the identities. Now we're going to use the identities to simplify trig expressions, right? Trying to make them as small as we can. So if I, for example, have something that says simplify sine of x times cosine squared of x minus sine of x. And it asks me to simplify it. I need to make this as small as possible. And I'm going, well, what can I do to combine these down to say one expression? Now, what I can see is that I have a sine of x here and I have a sine of x here. And so I can factor out sine of x, right? I could write this as sine of x times cosine squared of x minus 1, because when I pull sine of x out of here, I'm left with 1. And I recognize that as being a trig identity or close to it, Like if I wrote this as sine of x minus 1 plus cosine of x, sorry, cosine squared of x wouldn't work if it wasn't squared. I can see that we're getting to what might be a trig identity. If I just factored that -1 out, I would have that Pythagorean identity. So I could write this now as negative sine of x, and I'm just factoring out that -1, and it changes the signs of everything in there. And now we have that trig identity, right? And we could write that as minus sine of x times sine squared of x. And if I multiply those together, I just wind up with minus sine cubed of x. And that's what we mean by simplify, right? We're trying to get it into its smallest form. It is a puzzle, right? You're not always going to pick the first thing correctly every single time, right? Sometimes you have to play with them a little bit and see what works. I am going to do a second example on this one just because I want you to see it. It's going to follow a similar pattern where we're going to use the Pythagorean identity to solve it. But I just wanted to make sure you kind of got a good read on it before I move along. Is everybody following? Are you getting it? Are you feeling it? Is it too early in the morning? Are you getting it? Okay. Kinda? All right. Sometimes it takes a little playing with it to fully get it, but so if I have cosecant squared of x, cosine squared of x times cosecant squared of x. I could have written it in the other way, but minus cosecant squared of x. Just cosecant of x, not squared. And we need to simplify this, right? Again, we are simplifying. This looks like another case where we can factor it out, right? On this side of the minus sign, I have a cosecant, and on this side, I have a cosecant. And I should not have written a squared in here. I'm losing my mind. Now, if it was squared, I could still factor a cosecant out of each of them, right? But I'd be still left with a cosecant on this side. So we are gonna start by factoring, right? And what we're going to factor out is what we have in common, that cosecant of x. So I'm going to write this as cosecant of x, because that's what I'm pulling out. When I pull it off of this side, I'm left with cosine squared of x. When I factor 1 out of there, I'm left with just 1, right? Because cosecant of x divided by cosecant of x equals 1. And again, if I rewrote this in the same form, if I rewrote this as cosecant of x minus 1 plus cosine squared of x, we can see that it's that Pythagorean identity once I factor out the negative. And it is, cosecant does work off of sine, so when we factor out that negative, it comes out negative on this side, right? If it was cosine, it would stay positive on this side. And we would get 1 minus cosine squared of x. If we apply Pythagorean pith identity, this would be sine squared of x, right? I could write this as minus cosecant of x times sine squared of x. Well, we're getting close. I know from the reciprocal identity, right? Here I can use reciprocal identity to say that this is minus 1 over sine of x, right? And I'm multiplying that times sine squared of x. And if we look at that, that's going to be negative sine squared of x over sine of x. And that is going to cancel one of these out, and I'm going to be left with negative sine of x, right? Because here I have 2 sines of x, and here I have 1, right? And 1 will cancel the other out, and I'll be left with negative sine of x. So it's some playing. You're going to be doing some playing with it. I didn't give you a ton of problems to do simply because I know that some of these can be time consuming. The first couple, you've got to find the 6 trig the 6 trig functions, and then the next couple you have to simplify these down to their basis form. I did give you more of these types of problems than of the first type of problems. The first type where you're finding the 6 trig functions, I only gave you, I think, 2 of those. And I gave, 8, 10, 12. I gave you 3 of those, and I gave you 4 of these kinds of problems. But I think you can get through it pretty well. Have your trig identities in front of you when you do them. That's going to be your best bet, because then you've got your trial and error. You can go, well, what do I have? What am I trying to get to? How can I get there? Right? And before we were doing it at the most basic level, and now we're kind of expanding on that a little bit. Any questions? All right, I'm going to end this now then, and I'm going to let you guys go play with it a little bit, because maybe that will wake up some questions.